Let's talk about the properties of sound. Some of this stuff you guys probably already know. Pitch. Pitch is a word that we use to describe how high or low a sound seems. Low pitch versus high pitch. You really don't want me to sing. I'm sorry. It's not going to be a good time for anybody. But you guys know what I'm getting at, right? High pitch or low pitch. So where does that come from? Well, it turns out that it comes from the frequency of the wave. Remember, frequency is how many wave cycles occur per second. So this red wave here is very low frequency. The purple wave down here is very high frequency. So if these were sound waves, waves of high pressure, low pressure, high pressure, low pressure, these were sound waves traveling through the air. This red one would sound very, very low, while the purple one would sound very, very high, right? Pitch is due to the frequency of the wave. I think that's pretty simple to understand. I have a little simulation here. I'll post this on the website, but here you can see there's a speaker. The speaker is vibrating. That's how speakers work, by the way. We'll talk about that some more, I think. They just very, very rapidly vibrate, causing the air to vibrate. And here you can see we have longitudinal waves going out to this man here. And I can, on my little slider over here, I can change the frequency. And I can also enable the audio. But there you can see my speaker is producing a pitch of 500 hertz. What happens if I increase the frequency? What's it going to start sounding like? Watch what happens to the wave. Yeah, now you can see that my wave has a much higher frequency, more waves per second. And what does it sound like? It sounds higher pitched, right? It's a very high pitched sound. So the higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch, right? So a very low frequency wave now gives us a low pitch. Different critters are actually capable of hearing sounds at different pitches. So here on this graph, you can see from 0 all the way up here to 160,000 hertz. This is a graph of frequency, a chart of frequencies of sounds. You can see humans, we can really only hear from 20 hertz to 20,000 hertz, which is actually a pretty good range. Elephants and moles and other things can hear much lower pitch sounds. We call those infrasounds. That prefix infra means below. So these are sounds that are below the range of human hearing. Of course, you know, dogs are capable of hearing at higher pitch than humans are. Those are called ultrasounds. Ultra means higher or above. So it's above the realm of human hearing. And bats and dolphins, of course, can hear very, very, very high pitch, high frequency sounds. Why is that so, do you think? Why have bats and dolphins evolved hearing sense organs to be able to pick up those types of frequencies? Well, it's because that's how they get around, right? They use echolocation to find their way around. So they do that by emitting very, very high pitch clicks. And the higher the pitch, the higher the frequency, the more accurate those clicks are, the more accurate those echoes are going to be for them. I'm not going to talk a lot about echolocation. That's just interesting that different critters, based on their evolutionary background, their evolutionary history, have evolved the ability to hear different frequencies. So all these animals can hear sounds that we would be not even aware of. Pretty cool. Another property of sound is volume or intensity, how loud the sound seems. We said that pitch, how high or low it seems, was due to frequency. This property is due to the amplitude of the wave, how much energy is in the wave, how much are those particles vibrating. If they have very low vibrations, if the amplitude is low, then that's going to be a low volume. If the amplitude is high, remember amplitude is distance away from equilibrium position. How far is that particle vibrating? If the amplitude is high, it means it's carrying a lot of energy. It's very intense. It's going to have a very high volume. Volume is measured in decibels. That's the unit of volume. It's a little bit complicated, but the decibel scale is what is known as a logarithmic scale. I'm not going to get into that really a whole lot. Basically, what you need to know is that an increase in 10 on the decibel scale would be 10 times as loud. So basically you can see here that a watch ticking has a volume of about 20 decibels. A whisper would be 10 times as loud. A refrigerator, you can see it's a difference in 20, would be 100 times as loud. Rainfall would be 1,000 times as loud as a watch ticking. A normal conversation dishwasher would be 10,000 times as loud. So that's what I mean when I say it's a logarithmic scale. It's a mathematical tool. You don't need to worry about it, but I just kind of need you to understand that the higher up you go, it gets louder and louder and louder and louder and louder. It's almost it almost expounds upon itself. So a shotgun blast would be way freaking loud. You can see that the human range of hearing is really this. We can hear not a whole lot below 10 or 20 decibels. Call a car horn extremely loud, and then at some point the sound gets so loud that it can actually cause trauma. It can cause pain, and it can damage your ear. I think you guys know that. That things that are extremely loud, all the way up to this point, you can see it says painful acoustic trauma, which sounds very, very terrifying. But of course, these things are going to hurt your ear because they're so loud. The particles will be vibrating so wildly. The pressure of the compression part of that longitudinal wave would be so much that your ear would get damaged. And now there's one property of a sound that I want to spend a little bit of time on. This is known as timbre. Yes, that's pronounced timbre. And this is the sound quality, basically what the sound sounds like. Now, if you've been listening and you've been kind of staying with me, you could probably ask this question all on your own, but I'm going to help you get there. I've told you that the pitch, how high or low a sound seems, is due to the frequency of the wave, and that the volume is due to the amplitude, and those are really the only two qualities of a sound wave that we can talk about. If the frequency changes and the wavelength will change, so yeah, there's wavelength, but that's tied up into pitch. So frequency, wavelength, amplitude, that's all that can really be changed about a sound wave. So think about this. Think about this. If you're listening to two different instruments, say a piano and a trumpet, and both of those are playing middle C, the note middle C, well, middle C is defined by the fact that it has a certain pitch, it has a certain frequency, right? So if the frequency of those two sound waves is the same, is identical, and maybe the sounds are being played at the same volume, the amplitude of those two waves is identical, then what can be different about them? How is it possible that we can still tell the difference between a piano, middle C, and a trumpet, middle C, and a flute, middle C, and a middle C sung by a soprano opera singer, and all these things? How can we tell sounds apart if that's all there is to their waves, if their waves are identical? The wave created by a piano playing middle C should be identical to the wave created by a trumpet playing middle C, which should be identical to the wave created by a soprano singing a middle C, right? Well, that's what we would think, but actually there's more complicated stuff going on. It turns out that whenever a sound is produced by these things, by anything in nature really, by your vocal cords, by a piano key, the horn of a trumpet, whenever sound is produced, remember sounds are produced by things that vibrate, right? My vocal cords vibrate, that sets the air around it in vibrations and oscillations, and that's the sound wave, so it's all about vibrations. Whenever something in nature vibrates to cause a sound wave, it turns out that more things start to vibrate with it. Here's what I mean. Imagine that you sit down on your piano and you play a middle C. You think that a middle C, produced by a piano, if we were to graph the wave, that it would be a nice smooth up and down pressure wave. But in reality, it looks like this. What the heck is going on? Why is it all jaggedy? Well, it turns out that, like I said earlier, anytime something is set into vibration, other things around it also start to vibrate. That's known as resonance. So not only do you have the string vibrating whenever you hit that piano key, that middle C, But the wood in the piano will also vibrate. The ivory of the piano key will vibrate. Um, the different parts of the string will vibrate very, very slightly. Other strings around it, even though you haven't touched their keys, will also vibrate a little bit, will be set into vibrational motion. That's known as resonance, when something that's vibrating causes other things around it to vibrate as well. So there's no such thing as a sound wave being produced in isolation. If one thing vibrates, if you strike the middle C on the piano and that hammer hits the string, it's not just that string vibrating. It's the wood in the piano, it's the other strings around it, the ivory in the keys, etc., etc. And all those waves that are produced, what do you think they do with each other? They interfere, and they end up adding together to create a very complex, interesting waveform. And so the middle C of a piano is not going to be a pure, smooth curve. It's going to be more interesting, more complex, because in reality, it's the product. The sound is the product of many waves, many things vibrating, causing sound waves. Those waves interfering with each other, constructive and destructive interference. And so we get this rich, complex sound, and we can all identify it. If you hit a middle C on a piano, most people are going to be able to tell you, oh, that's a piano that you're playing, because the wave pattern is complex. Because everything else in the piano is also set to vibrate, which causes their own little tiny sound waves. That's known as timbre, the quality of the sound, what it sounds like, and it's due to the interference of many different sound waves. Here's a middle C, the graph of a middle C. Remember pressure, right? The pressure wave of a middle C, or I guess this is C sharp, isn't it? I don't know much about music. Anyway, the graph of a C note produced by a perfect computer. So this is what it would look like. Well, here's the graph of that exact same note produced by different instruments, a flute, a piano, and a trumpet. You can see how different they are from each other. The flute is pretty smooth and normal, but it still has some irregularities in it. The piano we've already discussed. Look at the trumpet, right? It's very jaggedy, very, very complex and rich. Why does this happen? Once again, because whenever anything in nature vibrates, it always resonates with other things around it. It causes other things to vibrate with it. The piano causes a lot of the other strings and the wood and everything to vibrate. The trumpet, all those brass pieces are going to vibrate differently and add together and create a very complex sound wave. That's known as timbre. Even your voices sound different than each other, right? I know you guys are all tired of hearing my voice. Sorry about that. You're only stuck with me for a few more weeks, luckily. But if I were to sing a perfect middle C, which of course I can, I just don't want to do it right now. If I were to sing a perfect middle C and you were to sing a perfect middle C, our sounds would sound different. There would be different timbres, different qualities of sound, because our faces are shaped differently. The sound wave produced down here by the vocal cords, the vocal folds in the larynx, that's what produces the sound in a human. Those vibrate. That's going to set the air in our mouths and our faces to vibrate, and yet that's going to resonate with all the structures in our face, our skull bones, our nasal cavities, oral cavity, the soft tissues in our neck and our mouth and our face. All these things are shaped differently for different people. They're going to vibrate differently. They're going to resonate differently. And therefore, they're going to add together to create a different, complex sound wave. So the idea that I want you to understand is that whenever we think about sounds out in nature, either voices or musical instruments producing sounds, things vibrating to produce sounds, we're never going to get a pure, perfect, smooth sound wave like this one created artificially with a computer. Instead, we're going to get something more complex, because in reality, one thing vibrating, the vocal folds down here vibrating, that is always going to resonate, set other things into vibrational motion. Everything is going to be producing its own sound wave, and those sound waves will add together to create a very complex and rich new vibrational pattern, new sound wave. And that's known as timbre.